question 1. This question is to find the enthalpy change of the thermal decomposition of calcium carbonate. However, we cannot measure this enthalpy change directly. Why? Because in order to get the enthalpy change, first we must get the delta T. So because we know that Q equal to MC delta T, if we're using a solution, we can get the temperature change in the solution together with the specific heat capacity of the solution and the mass of solution. After that, we'll get the heat, the Q. So then we can get the enthalpy. So negative Q over 1000 N. N is a mole of the limiting agent. So for this thermal decomposition, it's very hard for us to get the delta T. Why? Because normally when there is a decomposition, so we will put the solid into the crucible, supported by the pipe clay triangle, and direct heat by the Bunsen burner flame. And during the heating, it's very difficult for us to get this delta T. Okay, that's why instead of doing this, so we can use two experiments to get the delta HR. So the two experiments that we will discuss is the reactions of the calcium carbonate with the hydrochloric acid to form the calcium chloride, water and CO2. So the enthalpy change of this experiment 1 is delta H1. Then another experiment that involve is the calcium oxide with the same acid form the calcium chloride and H2O. So the enthalpy change for this experiment 2 is delta H2. So by using these two enthalpies, we can get the enthalpy change of the reaction, this one. Okay, later we discuss using the calculation. Let's go through the steps. For experiment 1, okay, step 1, weigh a 0.05 mole sample of calcium carbonate solid, and after that transfer 50 cm cube and excess of 2.0 mole per dm cube hydrochloric acid into a small glass beaker. From here, we know that the acid in excess, and therefore the calcium carbonate is a limiting agent. So means later when we calculate the enthalpy change for this experiment 1, we must use the mole of calcium carbonate, as now it is a limiting reagent. Okay, step 3, start a timer and measure the temperature of HCl in the beaker for every 30 seconds for 2.5 minutes. Means there will be 5 temperature readings before the solid added. Okay, step 4, after 3 minutes, add the sample of the calcium carbonate to the acid and continue measure the temperature of the reaction mixture for every 30 seconds for a further 5 minutes. Okay, something like this. Add the calcium carbonate solid into the acid and we measure the temperature. And we can get the delta T from the graphs later. Once we get the delta T, we can get the enthalpies. And for experiment 2, the steps, they are exactly the same. It just the solid used now is a calcium oxide. Part A, suggest why enthalpy change of the reactions for this thermal decomposition of calcium carbonate cannot be measured directly. Okay, this one I already told you. Because the temperature change, the delta T, it cannot easily measure during the heating. So as a calcium carbonate is being heated at the time, very hard to get the delta T. part B1. Calculate the mass in gram of calcium carbonate being weighed using 2 decimal place balance in step 1. Okay, first you need to get or calculate the molar mass of calcium carbonate. So it's 100.1. After that, just use the mole times the molar mass. So we get the mass 5.005. Because it's mentioned 2 decimal place balance, so the mass of calcium carbonates that need to be measured is 5.01. So you must put 5.01 gram there. Part 2. Outline how a student would weigh by difference using a weighing board in order to determine the exact mass of calcium carbonate added to the acid in the pickle. Draw the results table with appropriate headings ready for the student to complete. Okay, so first, we know the theory mass that need to be taken is 5.01 gram. So we just add about 5.01 gram in the weighing board. After that, we need to weigh the mass of the calcium carbonate and the weighing board. So this is the first mass readings that we must take. Okay, after that, the solid will pour into the acid like this. Okay, so means the calcium carbonate in the weighing board, okay, pour into the acid. So in the weighing board, so there will be some residues there. So we need to take the second reading. After the calcium carbonate added to the acid, measure the mass of the residue on the weighing board. Okay, of course, together with the weighing board. Then we get this second mass reading. So basically, we need to measure 2 mass. So the mass of calcium carbonate with the weighing board. After addition, then we need to weigh the mass of residue with the weighing board. So we use the first one minus the second one. So we will get the mass of calcium carbonate added to the acid. So this is the actual mass of calcium carbonate that added to the acid. Okay, of course, for some of you who not really sure what is the weighing board, is something like this. It's normally it's a plastic. We just put the calcium carbonate on in this weighing board, and we pour to the acid. Part C. Identify which piece of apparatus should be used to measure the volume of HCl in step 2. And give a reason for your choice. Step 2. Let's get back to the step 2. Okay, step 2 is transfer 50.00 cm cube of the HCl. So because here already mentioned 50.00, so means you cannot use measuring cylinder. Okay, because we must use the apparatus which can measure until 0.00 or 0.05. So the apparatus that we should use, of course, now is a burette. Okay, burette should be used and is measured to nearest 0.05 cm cube. Okay, that's the apparatus that need to use, even though the acid that we use is in excess. It just based on the step 2 instruction, so we need to use the burette. Okay, part D. Without making any changes to the apparatus, suggest an instruction to be added to step 3 and step 4 to make the experiment more accurate. Step 3 and step 4, there is a missing instruction. Okay, so this one is before the solid added, and this is the after the solid added. So it should be stirring there. Once before the solid introduced, okay, it should be constant stirring, and the temperatures that measured might be more accurate. After the addition, of course, the stirring must be there. Then we can get a more accurate temperature. Okay, so the answer is quite straightforward. Stir the mixture or measure the temperatures more frequently. Stir the mixture is better. Okay, part E. So we have this table 1.1. Data already given. First 5 reading before the solid added. This one is the 3rd minute. Okay, no measurements taken. So after that, the temperatures measured until these 8 minutes. Okay, part 1. Plot a graph in this figure 1.1 to show the relationship between the temperature and the time. Just use all this reading, all these the results to plot this graph. So if you follow this the results, you should get something like this. Okay, so first you must get the, okay, let me make it smaller. Okay, so first you must follow all the plots provided. So 10 points plotted, and after that you must draw a line of best fit from the 4 minutes to 8 minutes. Okay, so do not include the 3.5 minutes. So the point at 3.5 minutes. Okay, this one is the abnormalist point. Do not include this one. So just draw a best fit from the 4 minutes to the 8 minutes. Right, make sure the best fit line is passed through as many plots as possible, and it must be balanced. Okay, after that, another one. Okay, we will get back to this graph later. Okay, part 2. Use your graph to determine the theoretical temperature increase at the 3rd minute. This one you must extrapolate. So this one is the 3rd minute. The minutes for the first line, already extrapolate for you, right, to the 3rd minute. So means once you draw the best fit here, right, so you need to extrapolate until the 3rd minute. So from the difference here, this point and this point, you can get the delta T. So for mine, I get about 19.5 degrees C. Right, so just get the difference. Okay, so again, for mine is 19.5. Okay, once we get the delta T, then we can use it for calculations later. Okay, part F. Suggest why the temperature measured at 3.5 is lower than the temperature at 4 minutes. This is very easy because the at 3.5, okay, because the powder added at the 3rd minute, within 30 seconds, the reaction still not complete. So that's why it's still increasing, right? So that's the reason. The reaction is not complete at 3.5 minutes. Part G. A student carry out experiment 2 and determines the temperature increase of 62 degrees C. The heat released by the reaction, Q is given. So we use Q equal to mc delta T. Where the mass is the M is the mass of the acid, and of course this is density, right? So the density of the 6L solution is 1 cm cube per gram, so or 1 gram per cm cube. So means 1 cm cube equal to 1 gram. So this is the meaning. And just follow the specific heat capacity given, 4.18. Okay, calculate the Q. Q equal to 50 because we use 50 cm cube. 50 cm cube means 50 gram now. Times 4.18 times the temperature increase. The delta T is 62 now. You should get 1295 joule. After that, use this heat, okay, to this equation. Delta H equal to negative Q over 1000 N. Over 1000 N means Q over 1000 means to convert the joule to kilojoule, right? So this part itself is kilojoule. Okay, this is the mole. So we must use the mole of the calcium oxide. Remember, this is experiment 2. So we must use the mole of calcium oxide. So it's still 0.05. Okay, so we get this negative 259 kilojoule per mole. Okay, part H. Use the energy cycle below. Your answer to G and the information given to determine the delta HR. Enthalpy change for the experiment 1 is negative 84 kilojoule per mole. Okay, so use this one together with the values here, the delta H2 here, or here, to get the delta HR. Okay, very easy. This one is the reaction. How we know this is delta HR? You try to see, we just cut these two. Okay, it's actually calcium carbonates from calcium oxide and CO2. So this is the delta HR. Okay, in order to get this delta HR, we need to use the two enthalpies from the two experiments. Okay, so go to this direction. So we know that it's calcium carbonate with acid from this salt, H2O and CO2. So this one obviously is delta H1. Calcium oxide with acid, okay, this one you just ignore this, just cut it, right? So point to this direction is actually calcium oxide with acid from the salt and water. So means this direction, this part is delta H2. So now we can use this H cycle or this energy cycle to get the delta HR. So sum up this one, delta HR plus delta H2 equal to delta H1. Follow this direction. Delta HR plus delta H2 equal to delta H1. Therefore, delta HR is equal to delta H1 minus delta H2, which is negative 84 minus negative 259. So we will get positive 175. Answer must be positive because thermal decomposition is always endo. Okay, part I, the last one. Identify the main weakness of the experimental procedure and suggest one improvement to overcome this weakness. Normally for the enthalpy's experiment, the main problem is heat loss. So this one also is the same thing, heat loss to the surrounding. How to overcome this? We can use two methods. We can simply just add a lid to prevent the heat loss to surrounding, or we can use because in this experiment is use a pickle, so instead of pickle we can use a styrofoam cup, right? So the heat loss will be minimized. Okay, that's all. Thank you.